To introduce our first lecturer of the mini course, Professor Fernando Fernandes Sanchez from Universidad de Sevilla. He will talk about integral characterizations of Poincare half maps and its applications to limit cycles of planar piecewise linear systems. Thank you very much.
Thank you. Hello. We must begin obviously talking about Marco. It's for me a pleasure to be here. Is Marco here? Not yet, but no, but it's very interesting. So I can tell things that he was here, then I will lose it. Okay. This is the place where I meet Marco in 2006. It's a wonderful hotel. A lot of people swimming in the sea or in the swimming pool, but we were here. We are mathematicians, so we in a small room with a blackboard. And I remember that Marco was talking about, this was the the name of the talk, families of periodic orbits of real systems. But I remember special equation with a third derivative and also the sign effects. They're a very small equation, but with something of behaviors amazing for me. So I was beginning then to study actual linear system because I come from smooth systems, clean information, global connection, etc. Smooth systems, and well, I see here a lot of ideas, new ideas of likewise linear system and non-smooth system that attract me to this world. Okay, let's come back here to this picture. It's a picture in special picture. This is me. Very important. Sorry. And this is Marco. It's important. And well, but there also this was in Bristol. One of the pictures that Mike showed this morning was in this meeting. And well, I have to choose this picture I like. I think that it is very nice. But the title of the talk has a lot of subjects that are related with the subject of this course. For instance, the inverse-integrating factors. I will talk now a little bit about inverse-integrating factors, Poincare maps, planar piecewise linear systems, and something that is probably the easiest way to deal with this kind of system. Okay, I think that we have this, at least now, the easiest way to work with this kind of Poincare half maps. Perhaps tomorrow someone will discover something new and it will not be the easiest, so probably. Okay, and something very important is that here it is the password, the Wi-Fi password of the engineer's house Bristol. If you go. Okay, so let's begin. The course has two different parts. One part where I will explain all the details, or almost all the details, and it is more like a course, a real course. And at the end, I will tell some of our last results. But I think that this is important one. So this is the first one. I think that I have 2 hours for this part, and the last part will be the applications. I will talk about an introduction. I will talk about inverse-integrating factors, also for linear systems, Poincare half maps, demonstration of the integral characterization, which is an important subject in my talk, and well, many other things that will be appearing one after other when they have sense to one. So let's begin the introduction, perhaps too long introduction, and well, I'm going to talk about Poincare maps for linear systems, but I think that it is important to say what is a Poincare map for a generic dynamical system. The first thing is that you have a flow, then you decide, you choose and hypersurface, which is transversal to the flow. And then, if there is a kind of rejection or something similar in the flow, then you will have a point of an orbit and the image, the first return map, and this is usually called a Poincare map. Usually, these kind of maps are locally defined, close to a periodic orbit or a homoclinic connection or something. And well, we know that fixed points of P are periodic orbits. If they are isolated fixed points, they are many cycles and many other things. So I have now marked this word because this is, I think that these are changes with the Poincare maps in partially linear systems. Why? Because we are not going to choose the hypersurface. We have one. Now I will show you. I'm sorry. It is not always transversal to the flow. It is the usual, but sometimes you will have tangencies or even worse things. And it is locally defined, of course, but we will try to study the complete Poincare map. That is the global study of this application. And well, this is the system we are going to consider. The easiest system, possible system, is linear. ISO is linear with two zones separated by a straight line that you can choose, for instance, x1 equal to 0. It's linear on both sides, and you know that assuming some conditions on the flow, we can define the half map, the Poincare half map, left half map or right half map, or well, in this case, we can take the maps in this way. You take here a point, and then a point, then the image, it will be the left Poincare half map, and then if you compose it with the right one, then you have the full Poincare. Or another possible thing, it is equivalent, is to take the point, to integrate forward, then we have the forward Poincare map, integrate backwards, and then we have the backward Poincare half map, and the difference between these two quantities are called usually displacement function. So let me tell you that the most usual way to use Poincare half maps is we have two systems that are linear, so what we have to do is to integrate these systems because we can obtain the expressions of the solutions, and well, this is the usual thing. But it has some problems. For instance, when you have to integrate the systems, then you need to separate cases depending on the spectra of the matrices. It is not the same to integrate an orbit of a saddle and an orbit of a focus or whatever. And also the flight times appear, and appears implicitly in these equations, and with no very nice expressions. So at the beginning of our research about this object, we decided, we thought that perhaps this could be removed. These problems could be removed in some time. This is the principal idea. How to override the difficulties? Well, the problem is to integrate the systems. The idea is not to integrate the system, of course. And if you cannot integrate the systems, what can you do? Well, the idea is to use an interval characterization that it will be the center of my course. Okay? And this, I put again this title of the talk. I have changed several things in interval characterization, and this is what I'm going to do. To explain the construction, properties, and some applications of this interval characterization. As you see, I have added here some friends because there are several people collaborated with me in this subject, and well, I have here something Perhaps it is not the best choice of colors, but it says something like comprehensive edition with exercises. I'm going to put several exercises, very easy exercises. And the idea is that please, if you want to learn how to manage this integral characterization, please do these exercises because they are interesting, they are simple. I think that I have made a good choice of exercises, but I'm going to do something. The exercises will appear during the talk, and I have a copy. I think that the organizers will put these exercises on the web page or someplace. I don't know exactly. And if you want, if you solve some of the exercises, you can send the solution to me, and then at the end, together with the slides of this talk, I will make a complete document with the solutions. You will have this in the web page, I guess, at the end of the meeting. Okay, and let's go. Well, this is the team. We are together. It is not usual to have just one picture of all the members, but yes, we were in a training. And well, again, this is me. Okay, this is because I was not sure if you were looking at the slides or not. Okay, and here's Dr. Victoriano Carmona. He comes also from the University of Sevilla. Dr. Isabel Garcia Medina, also from my department in the University of Sevilla. And Douglas Duarte Novas from UNICAM. I don't know where. Okay, and I think that I had forgotten to add a doctor here. Doctor stays in my So from now on, I think that I'm going to use these abbreviations to talk about us. And let me tell you that in order to understand who is who in this picture, I think that Victoriano, perhaps he has given the 50% of the ideas and the results of this theory. Garcia Medina Elizabeth was working with us just a little bit of time, so I think that a 5% is okay. And Douglas is working with us several years ago, and I think that 45%. And well, I am here because I'm handsome. In Portuguese, eu sou muito bom. For me, it is very difficult to speak anything in Portuguese. Sorry, I don't know why. I'm not prepared for this. Well, I thought it's my problem. Okay, so what I'm going to do now is to tell you a little bit of the chronology of this research, because at least for me, it has been important. What we do here is we are not solving all the problems of mathematics, but we are doing something that it is a little bit new. And it is a way, you are going to see this now, it is a way to study some usual problem in a way that it is not usual for our colleagues. And this is not very easy, because you tell to a colleague you are doing the same that they are doing, but following another approach, and sometimes they don't accept the idea, at least at the beginning. When you explain it and then you see that it is working, then all of them are happy to have another approach to the problem, but at the beginning it's not easy. So I think that it is important for you, at least for young people. For young people, I have seen some ugly faces. Someone said youth is not a question of age, it is a question of speed. I don't know who is, but I guess he was very young. Okay, for young people, for young researchers, to see the difficulties and the road to to this final result I will show you during this course. Okay, for us, 2011 was the moment when we met for the first time with the concept of inverse integrating factor. This is a very important subject. It's a very important object for planar for planar systems in general, for small systems. But for me was unknown, and this was during a talk in a meeting in Argentina, Huelva, about normal forms of planar systems. It was a talk by this colleague, which is Cristóbal García, and well, I had added this picture because they are together with Marco, not in this meeting, in the previous meeting, the one with the good hotel. But well, Argentina, this was another meeting. Argentina is also a very nice place to visit. They have a very good food, very calm, and they have also a very nice cave with small halls and big halls and small corridors. Very nice. Here we have a picture. Perhaps you cannot see it very well, but Douglas, Victoriano, and me with our family. The small Douglas, which is called Gael, and the small Fernando, my son, which is bigger than me. So that's a strange thing to explain. Okay, so after this talk, we try to use the inverse integrating factors to see something new about this famous work about the system of three limit cycles in Weiswald linear systems. It was not successful. It was a beginning. We follow some ideas of this work by Jaume Gibre, Tony Terrell, and Lumière, and well, the first integrals that they used in this place. But what we thought that this was not the way to solve this problem or to improve this problem in some way. So we decided, Victoriano and me decided to study more about inverse integrating factor. It's very important. If you want to apply something, you have to study something. But the important thing was this. Victoriano became ill, was a contagious disease, so he had to be isolated, he had a lot of time to study, and then he had a lot of good ideas about how to apply these inverse integrating factors. So our first approach to our characterization appeared more or less this year. 6 years more, we were still continuing refining and improving the integral characterization, and our goals were to, as I had said at the beginning, to reduce as much as possible the cases and to find common definitions and properties and also proofs. And well, the principal problem always is to talk about the maximum number of limit cycles, to obtain upper bounds for the number of limit cycles that a planar Weiswald linear system may have. In these years, Elizabeth García was helping us with some properties at the beginning, but she decided to do other things. And also, Douglas joined the teams in 2016, and it was a good impulse to study limit cycles. We gave a lot of talks trying to convince our colleagues that this would work, and well, the idea to me was the one that I have showed before. The integral characterization is probably the best way to deal with this kind of systems. Well, and this was at the end of 2019, which we made the first two manuscripts. 2020, COVID, we still working this, but obviously meeting online, and something that perhaps you noticed is that the management review procedure was considerably delayed. So we had to wait for another year, to publish these two first manuscripts. In the first one, we described the integral characterization, and in the second one, we proved with a simple proof we were able to prove again the Bloom-Schwarz conjecture. I will talk about this during the course, so like this here, and then as we see that this was working, we decided to do other things. We study other objects, period anomaly, invariant manifolds, resultants, the result of polynomials, etc. We began to study the results about polynomials by Kovansky. This is an interesting work. I will talk a little bit more about it. And we still were working with upper bounds of these cycles. And that to end, we still give more talks. Something that I want to tell you is that from the beginning, the first idea of university de facto to the first publications, well, it lasted 10 years. So for young researchers, you do something like this, but we were doing other things, of course. But for young researchers, perhaps you have a good idea. If you have to develop it, if you have to refine it properly, etc., you will spend a lot of time. Please don't give up after 2 or 3 years. Go on with the research. Okay? And then let me tell you that this was a good year because we published 4 new papers, 3 new papers. One of them about the period anomaly, another one about properties of the integral characterization, and I think, sorry, 2 more, just 4. The upper bound for the non-sliding sliding case, and the one that I think that it is the most important, this one where we give an uniform upper bound for the system of limit cycles for isolate linear systems with a straight line or separation line, which is a straight line, but without any other conditions. Okay, and now what we are doing now is we have some conclusion. Integral characterization works. This is the reason why I'm telling you this in this course. We have seen that the common reassignment allows us to find parameters that are common to all these cases for the linear system, the binomial linear system. But if you do the study separately, then you can find the parameters. Perhaps you find the parameters of expression in one of them, or perhaps in the other. But to have a complete vision, you have to do it together. Something very interesting of the integral characterization is that some problems are not polynomial, can be written as algebraic equations via this integral characterization. And well, now, following an idea by Armengol, we are trying to apply this. We are going to the beginning. We are trying to apply this now to particular cases. We have devoted a lot of time to common cases, now to particular cases, and we have something to say about this paper and some other order, but this will be at the end of the talk. So well, I think that I have finished the introduction, perhaps a little bit long. Something that is very important. This is a course. Please, if you have any doubts, you have to interrupt me. Not only wait till the end. You have to interrupt me and to ask me. Please, my idea is that at the end of this talk, all of you know perfectly what I'm going to tell. Okay? Okay, well, let's begin. The first idea, inverse integrating factors. Just a few ideas about this.
Just to say that the last paper you quote is the first paper where
Yes,
they proved that they had 3 clean cycles.
yes, I had to speak a little bit about
They
this.
show an
Oh,
example.
yes, but this is just an example because we have another 2 examples. Okay, I don't want to say anything new. We'll expect until the end. Okay. Well, so what is an inverse integrating factor? For a planar system like this, smooth system, the system can be written in this way. This is the audience trajectories, or this way, the one you prefer. An inverse integrating factor of this system in a region of a plane is a function phi such that has the continuous derivatives, is not only null, and satisfies this PDE. This is an inverse integrating factor. How you are thinking, why is this an inverse integrating factor? Why the name inverse integrating factor? Well, exercise. This is the first exercise. This is called an inverse integrating factor because if a function v satisfies this equation, then 1 over v is an integrating factor for the equation of this one. I have written this line, okay? That is, this equation is exact. This is something that you can do. It's very easy. Moreover, something important that we have to keep in mind. This equation is exact, then after the change of time, this one, then the system can be written in this way. Like, and this is a Hamiltonian system. This is important to apply in some moments of our theory. Okay. About inverse integrating factor. There's some properties because we are not doing an analysis of these objects. We are just using them for our. Here you have a lot of references by Giacomini, Libre, Piano, Chavarrica, well, a lot of people, Isaac Garcia and Rao, but many people. And for instance, limit cycles of the systems, if they exist, are included in the set of the zeros of this inverse integrating factor. This has something to do. This can be very easily proven if you take into account that if you have an inverse integrating factor in a region, as you have to divide here by this integrating factor, the integrating factor cannot be null, this cannot be 0, and then since this is a Hamiltonian system, it has to have a limit cycles. Then if the system has limit cycles, they must be here. That is in the place where the inverse integrating factor vanish. Okay. Yes, this is important also. It is defined in a neighborhood of a hyperbolic saddle point, and then the v vanish on the separations, that is on the invariant manifolds of this saddle. And well, if you are looking for homoclinic connections or heteroclinic polycycles in general, v is also going to vanish. But in linear systems or partial linear systems, like the one that I have shown before, we cannot have very complicated polycycles like this. But I will talk something about this during the course. And well, this is a property which is also very interesting, is that if phi is the flow of the system and f is the vector field of the system, then you have this relationship between the value of the inverse integrating factor in one point of an orbit with respect to the initial point of this orbit, and this exponential of divergence. For us, it is also important because in our system we are going to see that this divergence is just a parameter, the trace of the matrix, and this will be used in some parts of the course. Any questions or whatever? No? Then, now we go to linear systems. Just linear systems. DC systems that we know. And I'm going to talk about inverse integrating factors and what can I have math for this kind of system. Then what I'm going to do now is to consider just one linear system. What I have put here, this is just to remind the previous slide. What I'm going to do is to consider this system, which is linear, and assuming some conditions of the flow, maybe that an orbital point in this separation line will come back to this one. Well, this is not a separation line, this is a section. Now it is a Poincaré section because the system is linear. But we are going to fix this section and we are going to study this left Poincaré map. If you want to study the right Poincaré map, simple change of variables will give you everything. So it is not necessary to do it explicitly. Okay, so the first thing, always that you have a system, if you can reduce the parameters, you have to do it. And if this is the system, and this is the Poincaré section, if you want to keep this section and to make change, then it is very difficult to reduce, as I told you, the number of parameters gives. First thing, we are going to assume this condition. This is not a restriction, because we are going to study limit cycles. If you need to have limit cycles, then Poincaré maps be defined. And these conditions, if m, this parameter is 0, then this system can be uncoupled, and then a Poincaré map cannot be defined. Okay, so we will not have limit cycles, so it is not interesting for us. So this is our first restriction. Well, under this condition, this system can be translated to this one, where here we have the trace, the determinant, and a parameter that tell us where the equilibrium is going to be with respect of x is equal to 0. In this change, the Poincaré section remains the same, x equal to 0, and well, it has several properties. Properties like it has an equilibrium for the different from 0, and well, it's invariant to this change. This is the change that you have to use to change the left Poincaré for the right Poincaré. And there is also a tangency at the origin. So we have a Poincaré section, but with a tangency. And I have written this here. This here, talking about this exchange of variables. You can find this word, but this is something that can be also checked here in this system. The behavior of x equal to 0 is for y positive, then everything goes to the left, and for y negative, everything goes to the right, and this is important. Well, then now an exercise just to prove all these things I have told you. Well, I have given you the change in the previous slide, but I think that it is a good exercise to know exactly or to compute by hand, if possible, these parameters in this general change of variables. For instance, as section, we want to keep the section fixed as x is equal to 0, then it is not necessary to add anything here, because they will change the straight line. So alpha 2 and alpha 3 are going to be 0. And if you put alpha 1 here, you give any value, then you can remove it with a simple change of time. So you can put here the directly at 1. Okay, this is the easiest part. The other part how to obtain beta 1, beta 2, beta 3 is the exercise. Well, you check that there is an equilibrium, prove the invariance, and study the flow from this equal to 0. Okay, as I have told you, I will give you all the exercises, also with the slides, with the definitions I will need for the exercises. And, well, I advance a bit more. About the left, one can have map. Go to trivial things. You know, one can have map. You have to take one here, and in some conditions you will ensure that this will intersect this line again for another value which will be called y1. Now, from now on, this will be our notation. y0 here and y1 here. Okay, this is the description. I have tell you, and well, this point is the image of this point by the left one. The time needed, well, something important that I was forgetting is that to obtain this, then you need a positive time such that the orbit will intersect here again. When I tell you this, because sometimes one forgets that there is a special point here, which is the tangency, where you can speak about a quantum map, but it has to be defined in some way. And in this case, if for this point you have an image, if for this point you have an image, etc., then you can extend the quantum here, the quantum map here to be the image of 0 is 0. But it is different if this is just a tangency or this is an equilibrium. Why? Because the flight time will not be the same. If this is just a tangency, not an equilibrium, then all these times will go to 0. So the flight time here will be 0. And so this will not satisfy the definition of the quantum map. So we have to add it this one. And well, this is the invisible tangency. And if you have an equilibrium at the origin, then the time is always the same. The flight time is always the same. So it is natural to extend this here with the same flight time. This is important in some details of the proofs. Perhaps I'm not going to talk about them during the course, but it is important sometimes. Okay. The question now is, I have been talking about inverse integrated factors because I want to apply the inverse integrated factors to linear systems. The question is there an inverse integrated factor for a linear system? The answer is yes, of course, it exists. And we have a proposition that tells that it can be found as a quadratic function. Okay? This proposition says that depending on the values of the parameters, you have different choices to inverse integrated factors. Then, for example, there are some bases, and the combinations of the elements of these bases will give you an inverse integrated factors for all the cases. Okay, but I'm going to remove now one of the cases. Two of these cases, and this will allow us to choose. I think that is perhaps the best option between all the possible inverse integrated factor, the best option for our problems. And well, now another exercise. So many exercises. I am not a good teacher. A lot of exercises, and I don't do anything. Well, I have written this in Latin, and later, so this is work. Okay, now exercise proves the proposition. The only thing you have to do, and it's easy, is to take a second order polynomial in x and y, genetic polynomial, and then put it in this equation, which is the definition of the inverse integrated factor, and then if you will have expression of polynomials equal to 0, and then the only thing that you have to do is to vanish all the coefficients. It will give you a system, I don't remember the 6 times 6 or 7 times 7, I don't know, a system with a lot of zeros that you have to solve. You have a lot of cases. Please don't put this in Mathematica, because Mathematica, I don't know now, but Mathematica is, cannot give you the result. I don't know why, but you have to be very careful because there are so many cases, and Mathematica forget some of these cases. I don't know in the last version, sorry, but this was something that happened to us because we tried to do it with Mathematica. We say this is not working, of course, because it was wrong. Okay. But you can do it perfectly by hand. No problem. Now we have to add a new condition, and this at the first one that was necessary to pass from the original system to the system in this generical linear form with the trace and the dynamic, etc. This is a new condition, but it's not an assumption. Why? Because if this is equal to 0, it is not possible to define the boundary of MAT. It's also an easy exercise. If this is 0, then you have y constant, so you cannot close the line in both directions. You cannot have a Poincare. Okay? So we put this condition, but this is something natural, and it is not a restriction for the existence of. It is not a restriction for our study because these conditions are necessary for periodic orbits and Poincare have not to exist. Well, if this case is moved, then the 4 cases are assumed just 2. And if you look at here, if you take this expression, this other one, for t equal to 0, these two inverse integrated factor, this basis, these 2 elements of the basis that allows you to construct the inverse integrated factor are included in this case. So I think that this is a very good idea to choose this as our inverse integrated factor. Okay? And this will be valid for all the cases that have limit cycles. From now on, in several slides, I will repeat this expression several times. But something about this inverse integrated factor. As I told you, the inverse integrated factor is very important for many reasons. But one of the most important things is that the zero set contains a lot of important orbits of the system. So we have to study the zero set of this object. Well, this is a second of the equation in x and y. So what you can find from here are just conic sections, and not all the cases. Okay, you want to study this, and well, the zero set. I'm not going to stop in all the cases, but let me tell you that if you have, for instance, a saddle, then the zero set will be exactly the 2 invariant manifolds of the saddle, for instance. If you have a degenerated case, then the straight line of this degenerated case has an invariant straight line, also appears here. Well, and something more about the inverse integrated factor is that you can write this way. If you see this determinant is just the condition for the eigenvalues of a saddle. And in the saddle case, you have to obtain the eigenvectors of corresponding to that saddle. this is the condition. If you write this expression, this will give you exactly this. So this will be valid, it's curious, it will be valid also for all the cases, or focus, or node, for all the cases, even the genetic cases. This is also an exercise. I think it's very easy, it's determined. As I told you before, the level curves of this inverse integrating factor are conic sections. And well, this is an interesting case because it's the case where the system has a focus or a center, and in this case the level curves are ellipses whose center is this equilibrium. Is the equilibrium. And this is important. This change transforms the inverse integrating factor into this expression, which is just x squared plus y squared. The level curves will be circumferences, circles. This is another exercise to make this change. This is useful when you have to make some computations in one or two slides. And well, in this case, this is a Lyapunov function of the system, because the divergence of this system is the trace of the system. Okay. So some properties about the inverse integrating factor and the relationship with the characteristic polynomial of the system is that well, both are given by expression of second order polynomials, second order, so they can be transformed with these changes, and then if you have the inverse integrating factor, then you can obtain automatically the characteristic polynomial and vice versa. Okay, but let's go now to the integral characterization. Okay, just to begin the ideas. I think that this is it. Well, what are we going to do? Remind, we don't want to integrate the system. Okay. So this is the system, written as a Hamiltonian system, because this is the inverse integrating factor of the system. This vector field here is conservative, and it is orthogonal to the flow. These are just these equations, we change the position and the sign. It's useful. Well, what we are going to do is to integrate, but without tiny the integral, of this field in suitable curves. The idea is if the point and the orbit and on the point of the map, the idea is to integrate this field, in this region, and to use the ring theorems or something similar. Well, this is the description, but this is just the curve that joins these 2 points. This is the segment that joins these 2 points. And there appear 2 cases, depending on where the equilibrium is located. It's inside, outside, or over this line. And then they have to be studied in separate ways, but at the end you will see that we will have a common expression for all the cases. Let me tell you, before doing the computation before doing everything, in this case, but we don't have anything here, this can correspond to all these cases for the linear system. So if you have to study case by case a situation like this one, you must study center, focus, the genetic equilibrium, node, result. If you have an equilibrium inside, then this can be focus and center. And if it is here, it is also focus on the center. Okay, so we are reducing all the cases to 3, and at the end, it will be just one expression. We are going to see. And let me finish with this. In the 5 minutes, yes, I think that at least with the first case, what we are going to do is to integrate the orthogonal and conservative field on this ray. And then this, the complete integral on the curve will be 0 because it is conservative. On this curve, this is an orbit of the system, the integral will be 0 because the field is orthogonal. And in this segment, you have this integral that has to be 0 because at the end all has to be 0. And this condition is the condition, the integral condition that y0 and y1 must satisfy. If you integrate now, you are wasting your time because our idea is not to integrate. Our idea is to time just this formula and try to use it to solve some problems. In this case, let me finish. I don't know, but in this case, since the equilibrium is here, is inside this zone, then we have to separate it from the rest with a small curve here. The interval in this purple zone will be 0. Again, I'm sorry, the integral in this complete curve will be exactly like in this curve. And if we compute the integrals, here it is 0 because it is orthogonal. And here this integral has this value. Okay, I have put this an exercise because you can do it taking the curve that you prefer, for instance, cycle. But this is not a good idea. Well, I did the integral, but you have to work alone. Let me tell you this, and I come back to the exercise. This is expression here. That is, we have the integral equal to this number. It is a different number, but this is an integral equal to a number. One thing that we are going to do is to derivate this expression, and then this constant will disappear. So both cases will be the same case. But this will be in some slides. And this is an explanation about the exercise. If you want to make this integral, it's an exercise to do it on the curve that you prefer. But it is a good choice. Do you remember the change that transformed the inverse integrated factor to this expression with x squared and y squared? Then if you make this change and you take this curve, for instance, that is an ellipse, then this integral is integrated. You can do it without any calculations. So a good choice in this curve may avoid you to waste your time. But I waste the time doing the integrals. And almost everything that is here have been done in 3 or 4 different ways. Yes, sometimes Toriano, sometimes Douglas, sometimes I were doing this computation because it is something new, and you have to be sure that what you do is correct. And also some numerical. Yeah. Well, I think that this is the place to stop. This is the last case, but tomorrow I will take here the problem and I will follow the explanation because this case is a little bit more special. And well, I think that it is the moment to stop. If you have any questions.
Questions or comments?
Tomorrow, if you don't ask questions, tomorrow I will choose someone and say, exercise one. Black one. This is not. See, I cannot believe this. Pero borré la. Yo voy a borrar. Voy a borrar. Cuando las tengas se las damos.
Hello. I have the pleasure to introduce the plenarist number 6, Armengol Gazul, Professor Armengol Gazul from Universidade Autônoma de Barcelona. He will talk about the different point of views about Hilbert 16 problems. This one is good.
Okay, hello everybody. It's really a pleasure to be here for this occasion. And I am always happy to be here with so many friends and colleagues. So this, at the very beginning, this is not a usual meeting. I wanted to talk about something where Marco Antonio is there. But finally I realized that I have no common paper with Marco Antonio. I don't know the reason. We discussed many times, but we have something in common. Because we spend time talking about mathematics. And so I have applied a B plan. This is another talk. I start with a B plan. This is another talk that I could have given, but I will not give. This is the title of the other talk, Applications of Montgomery-Wagner's Theorem. So what is saying this theorem? This theorem is a very important topological theorem that is that if you have a periodic map, meaning a map is periodic if by composition gives the identity and has a fixed point, then around this point you can linearize the map. So there are all, even in any dimension and in any class. So this is, in fact, it's a very important Montgomery-Wojner theorem that is of Wojner, not of Montgomery-Wojner. And Wojner did the theorem in the 45, and Montgomery published a book with the theorem. So using this theorem, that is in particular for involutions also is very useful, we did these three words. So the talk will be to explain all this. But this maybe is too old. But the point is, who explained us this theorem? So Anna and me were here trying to do mathematics with our team of Brazil, and we were talking with Marco Antonio. Yes, you are right. Marco Antonio take us and say, do you know this nice theorem? You have to go to our library, and there is the book. And hello, I was talking about you. Just arrived at as always at the right moment. Who explained it us this year? So this, Marco Antonio says, yes, this is this very beautiful theorem, and we say, but we don't want the statement, but the proofs, yes, you go to our library, this book is there, you can study. We studied this book, and we got here, there are some more technical results, but I like a lot this result, that is a non-integrability result, that is not an non-integrability. You prove that there are no first integrals. And the key point was this. But this was, we didn't know nothing about this. So this is the point. We spend a lot of time talking about mathematics. We learn a lot. Especially I learn a lot from him. And this collaboration is not only based on this second part, but in the first part. It's very important. So, happy birthday and thank you. I had also prepared the same that in the first talk, because I was tempted to put here, because he is at my level. So I can put him because we're friends, and Ronaldo, but maybe he's a good place for him also. Okay, so these are the fathers of many things. There are other fathers here. From our side, it is not symmetric. On the other side, only one father. And maybe these are the fathers that we are here, and that we are doing these nice meetings and spend so many time. So now finally, because of I decided to talk on something that I am really doing now, not all. So this is the actual, so the talk starts now, and this is so new that it's not done yet. So it's publicity into. So this is the point is, I will talk about Hilbert's 16th problem. So this is, I will talk about the 16th Hilbert problem, but not the usual way to say all definitions, not my way. Then statements in real and in complex, you will see the difference in a moment. And then proofs. This is not technical, this starts to be more technical, you will see. So, this is a Hilbert problem is very difficult. You don't need to read. And we don't know how to do, so we try to find different ways of approaching it. So I changed the problem for another problem that if I solve the other problem, I am done also. But this, and the point is, control the number of limit cycles in terms of the number of monomials. So for the Hilbert number, this one, today, only for this talk, forget about this number. The degree, I don't care about the degree. I only care on the number of monomials. And the problem is, can you do, this gives you something new, can you understand better the problem? So I understand to fix exactly this system. You don't see the 23. You only count 1, 2, 3, 4, 5, 6, 7, 8. So this is a system with 8 monomials. And this other system, don't look at this. Only this is a system with 3 monomials. So the new problem is systems with 8 monomials. How many limit cycles can have? Maybe have degree 1000, 1 billion. No bound for the degree. Just to fix the ideas, we already know this. Forget about differential equations, think about polynomial. Think about Descartes. If you have a polynomial and written in real coefficients, the number of roots is 2 times the number of monomials of the polynomial plus 1. Don't care about the degree. You have a polynomial of degree 1 billion, but has 7 monomials, has at most 15 roots. The degree is not important. But in complex, the degree is important. In Hilbert problem, we are studying things with the degree, but are in the real, maybe it's not a good number. This is, okay, it's good, but maybe it's not the more natural. Or maybe I don't need to put this is a two-monomial equation that has 2 real solutions, but n complex solutions. This is clear. The idea is maybe something like this happens. We will see that somehow something like this happens. Now we return to differential equations. In real form, I am not saying that a system with m monomials has, I don't know how many, because if I did this, I would have here some medal, and because it's equivalent to the, I don't know, but I feel that it's true. The number of limit cycles depend only on the number of monomials. But of course, you will see in the proof that there is no statement about this. Is this recording this? Is this? So I feel no. I think that maybe could be true that. And in complex form, we will see that the complex forms, it is true. The number of monomials is not relevant. So the real and the complex. So let's pass to the results. All this problem starts in a paper that is in the thesis of Jacob Carvalho. We did with Claudio, where we started this point of view. We proved this, we start very happy because systems with 0, 1, or 3 monomials have no limit cycles. This is, you can prove this is not the case with 3, is a little more involved, but you see 3 monomials means x dot equals 2 monomials and y dot 1. There are many cases, many degrees, but you can manage. All of you could do this if you want. Here we found at that moment this lower bound. So that increases, there are at least this n minus 3. And also using the results of classical of linear equations and other things, we prove that this number, this is the Hilbert number, but we call Hilbert monomial number. the M of the monomials. And of course the variable is M, monomial. And this was the statement when we start doing this work. And we proved that this monomial number increases quadratically. So this is what we present here. Here before we knew that increases M log M. This was known. This was writing the things in a different way, all the known things. This also follows as a consequence of the n squared log n for polynomials. Using this you can arrive to this, but you lose one m here in the. But here I will give an idea of the proof why it increases quadratically. Of course, this is hidden here. I am trying m squared log m. This is natural problem. I think interesting, not easy. So ideas are welcome, but it's open. I open to everyone do this for me better. Great job for me, because this the new result is that you increase quadratically. In fact, this is the lower bound is a little better, but this is lower order, so no problem. Maybe I want to fix in this table first. This is the situation. Then I say some words. This was before our talk, but before our work. But these people does not care about monomials. This is a translation of known results from our point of view. From here is very interesting. This 24 was done in this proof, computer-assisted proof. This 24 is a nice paper with a computer-assisted proof with a system with 24 limit cycles. But they didn't care about the monomials. But it turns out that they use a system with 9 monomials. We had this in mind when we started. Finally, we arrived here. This is our theorem. Each one is a fight against. This one is the general theorem, the best result, but I have to talk a little. I have to talk a little about each one of these numbers. Of course, if I don't have time, I will stop and talk. I prefer to explain slow. This 4. I alone first 1 year trying to prove that here appears 1, because I thought 0, 1, 2, and 3 monomials, no limit cycles. So 4 monomials, 1. I found 2. So say 2. 2 is 2. I went to a meeting and I talking with someone, not talking with someone, I say, I have these 4 monomials and I'm very happy because I have 2 limit cycles, I am preparing passes from my side. What? And this was Hofbauer. Hofbauer did something that I didn't know at that moment, that this system count monomials, 4 monomials, has 3 limit cycles, 3, more than my 2. But these numbers are real, because they study another problem, they invent another problem. This is called S systems. This is, I invented this name and did this in the first quadrant. But talking with Hofbauer there, we realized, but if you take rational numbers tending to these real numbers and you do a clever change of variables, maybe you can arrive to a polynomial 3s. And moreover, what happens, I only use Blackboard here, is that you have this was S systems only defined in the first quadrant because are real powers. Home power found 3, but the symmetries gives this so this is the 12. So it's, and I'm convinced that 12 is the maximum. But who knows? In limit cycles, this is like the 3 plus 1 of quadratics or this kind of problem. But it's very interesting. These two 12s you don't do nothing. It's the same. So these two, sure that probably are better, but we were tired because then this 16, 20 are found using all I know of level of quantities are different way. Always multiple of 4 because the trick is in one quadrant multiplied by 4. And these two are from our theorem, so each one has his own, but this is the result. And because, I don't know, you have seen this is publicity in nonlinearity. In nonlinearity they say, okay, but this is very nice, but where do you apply this? And we were prepared. So I have always applications in the system, in the meeting that I attend about these chemical reactions. It turns out that each monomial is a chemical reaction. This is a few words, this is what happens. So if you study people that study these chemical reactions, and indeed they are interested in this monomial system. So we win, we convince the referees this is a good application. You can read about this. It's not a false application, it's an actual application. In complex, I decided, I know that here I have 2 talks, but I decided to combine because I think that is the surprise real against complex here. Complex. We started again, one more complex monomial is homogeneous system, so have no limit cycles. Maybe centers, but no limit cycles. Then we spent, if I am right, 3 years proving that systems with 2 monomials have at most 1 limit cycle. It looks like very simple system, but these systems have hidden a lot of critical points, symmetries, centers, saddles, many. So finally we succeed. But before we have done, we had this paper with Cencili and Joan Torregrossa proving that systems with 3 monomials have no upper bound. So clever your mind. Now the number of monomials is like in equations. The number of monomials has no relevance at all. So of course here we have a double index problem. I introduce this, I have no more letters, I don't know. H, J, N. This means N is the number of complex monomials. No, so J is the number of complex monomials, and N is the degree. I need both because for these systems with 3 monomials, there is no upper bound. So the upper bound is double. You have 3 monomials, and inside all systems with 3 monomials, which is the upper bound? Depends on the degree. So this is a very particular Hilbert problem.
This was in 2015?
Yes, before. This was the beginning of all. Because I wanted, my idea was to prove that this maybe has some bound, but I have the idea that this is easy, I will do later. And what's easier, this. We start proving that here there is no upper bound, but maybe, who knows here? Because here it's possible to have n points of index plus 1. So around each one of the points, and there are points of index plus 1 minus 1 a lot, and you can have limit cycles surrounding several points, so it's not. So this is correct, 15, 23. So in this notation, this was this old theorem that this Hilbert number means 3 monomials, degree n is at least this one. Here is the case of quadratic, I say quadratic 2 monomials. So the goal was improve this lower bound. Of course, if you cannot get the upper bound, perfect, but at least is this, maybe it's quadratic with an I don't know. And the second one, study, this is an open case, you will see now. So first result, we will prove that we double the number of limit cycles. The previous example have this number, and we get this number. The difference is here we use abelian integrals, here we use Lyapunov quantities. And this is also very nice that this is also open. So it's the easy open problem about limit cycles that I think in the world is you take quadratic systems. Inside quadratic systems is open the number. You know, every people thinks at most 4 limit cycles probably, distribution 1, 3, all this open. But now take 3 monomials inside quadratic system. I put here one example, 3 monomials. Inside this there are 20 families, is 6 over 3. These 20 families, there are 2 trivial ones, that's the linear one, no limit cycles, homogeneous, no limit cycles. So remain 18 families. So we succeed to order, and we use this notation, take 3 monomials. And these are the 18 cases. So these are all are quadratic cases, but of course not all quadratic cases are here, because here are, if it appears this inequality is that we prove that in this case, for instance, systems that has z squared, z bar squared have at least 2 limit cycles. And if it appears this greater or equal than 2, means that I don't know how to prove that has at most 2. So here you see 0, 1, 1, 1, 0, 0, 0. So this is more or less only remain these 2 cases. And these 2 cases we prove that this is equivalent to this one. So only remains 1 case. So this is the easy system in the world, open. Means 1 zeta bar, zeta squared. Warning, half China is working on this. The other half is working on that. This is more difficult, these are the ones that are stronger. Here is the more difficult, but someone brought me, we are trying to complete this file. Nobody talks about this for the moment. So, this is, we prove here that this, for instance, this is very nice. This is a proof. At most 1 plus 1, and this happens. Also, this is a proof. So I have 10 or 15 minutes more, I think. No? 20. Oh, perfect. So I learned from nonlinearity applications. Always, you have to put. If not, the referee is very easy to say, what you are doing is has no application. So I put applications. Of course, the famous system, most famous system are these normal forms of. You use the trick and advices for young people. Use the trick to put a famous mathematician, and then say Arnold says that it's very important. So you don't need applications. Arnold is interested in this, and the problem of limit cycles of this system with Q different from 4 is solved, but Q equal 4 is yet open. This is, we're talking about 5 limit cycles, I think. So this is fulfilled. It's very interesting, the problem. So what you do with 3 monomials is interesting by definition. By definition. We can use, start use Marco Antonio, this. Don't use me. Don't yet use me. Maybe never. Okay, so now I start to give the ideas of the proofs. We start to give this part is only not technical. Here, not really more. So start. I decided to explain not all the constructions, only the general, the quadratic increase, that increase quadratically. And all is a consequence of this very specific result. That I will show you a system with this number of monomials. You will see why I've written in this way. With this number of limit cycles. This is the point. Here, you put in then R, you see here a product. You put R, n over 2, and this gives the quadratic. So I don't care about this part. This is, you see the quadratic in this product. When you have this product, you see the tools are not new. I use the Poincare-Mondragon theorem with abelian integrals. This, but really, I don't use the classical one, but I use a version that in fact is from Colin Christopher, the version that I will use. This is, maybe I recall, this is the classical one. You have a Hamiltonian with a perturbation and saying that you construct this integral that talking fast is an abelian integral if h is polynomial. And then this integral is the same that this double integral by Stokes theorem. And this function depends only on the energy, and the simple zeros gives limit cycles of the perturbation. This is the one that I will not use. And this is the version that I learned from the paper, the famous paper of n squared log n of Colin Christopher and Professor Lloyd. That is saying, some Bolzano say, if you have an interval and you have a change of sign and you are in the wall, analytic wall, we are in the polynomial, so no problem, then you have at least one limit cycle inside. It's not the same. Does not say nothing about the hyperbolicity, don't care about this. So we use this second, not less use it, but sometimes for some problems it's much faster to do in this direction. I am not saying that I cannot do the same with this part, but here is much better. So the idea is, maybe some point, I pass very fast because I want to say you many things, but I don't say that the real part is done with Paulo Santana, that is here, from here, and the complex part is done with the team of collaborators of Mallorca. We are, okay, you will see, but I am not doing this alone because it's much interesting to do with other people. So here is, you see here is the system, this is study, this is our example. Of course, this is very simple example, and with this simple example, we got m squared over 2 at the end. So this is, you see the Hamiltonian is very simple. This one, y minus y to the third, and here a symmetric one that has r plus 1 monomials. So this has r plus 1, r plus 2, r plus 3 monomials, and here I put n monomials more. And this is the total number is n r plus 4. This is the n plus 3 of this. No, here gives r plus 3, and this one is n plus 1. So this is the structure. But I don't care about this number. I only prove the important part because this is only low order for bounds. And here, this is the system. I choose here R equal 2. And you see here the starting point. The system has this system, the R2 and 1 is a particular case, but all systems have many points in this line, the 1, and many points in the -1, and many points in the axis. Only these three, because of the first equation. Here you have center, saddle, center, saddle, center. Here saddle, center, saddle, center. And I only mark only use these colors, just to see that are there, but I will not use this. I only will use these 6. I want to give you the trick of the proof that is very easy. So this is the more technical part is here. So I have to study this. This is unperturbed. The idea is that with only one parameter of two parameters of perturbation, I get one limit cycle here, at the same time, 6 limit cycles. With the other parameter, I get 6 more, and 6 more. In this way, each time that I put one monomial, I multiply by 6. This is the idea. But how you do this? Remember that we have to compute the integral, but the system is very particular. We have to compute the integral of this, only this. So, but this one, now I will choose one special. This has to have n plus 1 monomials, but I choose first, like by induction, I start with only 2 monomials. This one and this one. So just to recapitulate a little, I start with this system, that this is the one that has all these centers and all these things, and I perturb only with 2 monomials at the first step. So what I have to study is the integral of this partial derivative. So it's here what I have to study. This is the abelian integral. And the trick, all the trick is how I choose this A1 and this M1. This is the perturbation. Because when I do the integral, this is the integral that I have to control. But remember that I have to control that there are some place where this is positive and some place where this is negative. If this is not here, it's positive because it's to x to the n. So I really need sometimes this is positive, sometimes this is negative. So I think these 2 orbits is where I will apply this Bolzano theorem. And then I take this value y that is passing between both. This is fixes this value. And then I have to do this integral. But notice that if I do in the integral in the smaller periodic orbit, this number is smaller than 1 because A is bigger than Y. Y is all times in the orbit and Y is bigger. So this quantity is smaller than 1 and there exists M1 says that this is very small. So the sign of this is positive. But if I do in the converse, in this gray region, this is bigger than 1. And this, with this power, this region, this smaller, bigger than 1 to some big power gives more contribution than this one and gives the change of sign. So now you have understood all. Because here you have integral negative, integral positive in the middle limit cycle. So in next time I don't expect you put another one. It means that there are here 3 limit cycles with constant. And this is very interesting because this is not a constructive. I don't know the degrees. But I don't care about the degrees because I'm studying the problem of economics. I know that there is one M1 big enough and then in the second perturbation and M2 big enough and this is okay. So this is, of course, I put more, you have more, and this is the part. Just now 5 minutes for 33.
90 minutes.
9. So n plus 1 you add more 4 times. I think that the idea is okay for the moment. Now the complex is other tools. But you know the tools. The idea here is we don't create, I forgot to say, there are no new tools. Only is looking at the same problem as always from different point of view, but unfortunately with no new tools, only tricks. Here I want to have a lot of limit cycles, but the point here is to find a good system to study. And after time, I don't fix the time, because seems that we are not very clever. After many times, we arrive to this system that has 3 monomials. You agree with this? Then this system has 3 monomials, but if you write in this way, you see that the critical points of this system are the origin and the end roots of the unity. So this works well. This looks nice, symmetric, so we are in the good way. So this is a system with 3 monomials that has the origin and the end root of the unity and the singularities. So the singularities are, you know the singularities. The idea is that because the singularities are analytic, because are the roots of the unity, you can study see if there is some bifurcation in these singularities. The singularities is easy they are prepared because we focus all of them. So, although it's not well located, this takes a lot of computations, there is a Hopf bifurcation. But there is some symmetry in such a way that you have a Hopf bifurcation in the end singularities at the same time. For doing this, we spend some time because maybe some of you, just for people that like a lot Lyapunov quantities, it's a system in complex variables. Here you have IZ, that is the normal form. The Lyapunov quantity is only this expression in red. So if a system is in the normal form, the linear part is in the normal form, the Lyapunov quantity, the first one, is very nice. But for a general system, that is our system translated to the root of the unity, the expression, this is the expression of the, you see the difference. No problem, but you have to compute, this is just to explain you that to compute this we spend some time. And it's something curious that it's not always positive. There are values of n that is positive, so it's more delicate. Maybe it could have been 0, so this, remember, this is 0, this is good, but because maybe you have negative charges, but not. So just this flower, the limit charges are like this. So there are 3 monomials, but there is one limit cycle, not a circle, but I found this on the internet is nice. In this example, you have this number of limit cycles in this distribution. So this is the last part of the talk is just how we prove the interesting parts here. The lower bounds are always done with Lyapunov quantities, nothing difficult. I only want to give some ideas of how to prove these ones here, not these ones. I have decided these zeros here and these ones here, just the idea of the proof. And remember that all the greater or equal are open problems. The zeros is usually much easier. You have the system, and you have these 3 systems. And for these three systems, what happens in complex is that the divergence is this expression. You can compute in this way, and there are the divergence here. So you see, divergence constant, so no limit cycles. Divergence 0, integrable, sentence. Divergence constant, no limit cycles. It's trivial. And the other one, this 1 plus 1, was done in an old Chinese paper, old, not very old, but 81. And the year 81, I was starting my PhD, I think. So maybe this is we use this theorem that saying more that this system with 4 monomials has at most one limit cycle. This is a homogeneous system plus a constant. But I don't want to, this is difficult to find the proof. I include the proof in the last slide. This is, in particular, all these cases are subcases here, so this is stronger than I wanted to. But I want to prove, the idea is, I like because it's based, I will use this one that is a classical result that quadratic systems with an invariant line have at most one limit cycle. This, I use this. This is, I don't have time to prove this. This is more available, this proof in many places. So this is, I'm sorry, but I was not able to find an easy proof in complex. So I am in complex, but now I pass to real. It's so, because this is the complex part. I want to prove this system has at most two limit cycles, one in one side of another and the other side. I did with small tricks. First, you pass the point, it's not restrictive, you believe me that you can do a change that pass this point here. In this way, you see that appears these two changed by these two. This is a translation, you can do this as change of state. Then when you are here, you do a rotation. This is very typical in quadratic systems, that you erase one term here. So you arrive here. Then I am here, this is the same as before. Now I change a time. And so I erase these two and arrive to this one. Here I make another, another change of scale. I put one here. And then here, a very strange change of variables. This is the clever one. It's possible that passes all one side of the plane to only valid in x positive and x negative. And you arrive to a quadratic system with a straight line. Because you see here 2xy, so x is invariant, and here quadratic. So here you have uniqueness, means that you have at most 1 and 1 in each side, and then by symmetry you have 2. So finally, in this way, we prove this 1 plus 1. And so this is all I want to share with you. This is the picture I take in my holidays this year. I like a lot. You have to, this is a commercial. Go to Azores. Beautiful, more than beautiful. And this is all. Thank you for your attention.
Questions? Comments?
In the complex case, when you have the roots of the identity, you have you said that you have a kind of a simultaneity where with the Hopf bifurcation, right?
All at the same time.
Okay.
Because there is a symmetric that is invariant.
It's symmetry. In the real case, you have some singularities distributed, and the abelian integral you have to compute. It's also the same for each one, or the.
Yes, but
you have this simultaneity too.
No, but there is different simultaneity. You see here that you have to compute this abelian integral, but on each of these curves.
Yes.
But the reasoning is that or goes to plus infinity, it goes to 0. So you don't have to care much. Only have to care in this term. Each one is different, but all are the same. There is no symmetry. Because this is different from this one. But the same are, you can arc, this is a finite number, you can do the same in each one. And there is a epsilon small enough that works for all at the same time.
Nice. Okay. Thank you.
More questions? No? Let's thank the speaker again. Now we have the poster section.
Well, good afternoon to everyone. It's a pleasure to be speaking here. This is a really important workshop for me. because since the first or second edition, I was present in some way in this workshop, just as a undergraduation student, as a student of Professor Medrano, and after that, I was always. I have been always participated of all editions that I could. Recently, I was not in the last one for technical reasons, but it's a very welcoming workshop, and I appreciate the opportunity of being here, speaking for you. And I would also like to thank Marco for all his contributions to the science and all his contribution to everyone who is here. And it's a huge pleasure to be part of this academic family. And today I am going to talk about bifurcation of a boundary hyperbolic singularity in R2. More specifically, I am going to talk about when I have one specific boundary equilibrium, we perturb the system, and we want to study when or under which conditions this perturbation can generate a sliding Shunikov connection. So, sliding Shunikov homoclinic orbit is a homoclinic connection through a hyperbolic saddle focus equilibrium of a smooth system. And under certain conditions, in the eigenvalues of this equilibrium, it is possible to show that this homoclinic connection is isolated from periodic orbits, or it is accumulated by countable infinitely many saddle periodic orbits. And also, there is chaos near this structure under certain conditions. In the non-smooth context, we can try to extend this type of connection in different ways. The simplest type of homoclinic-like connection, homoclinic Shunikov connection that we can think in this new context, is a homoclinic connection through a real saddle focus equilibrium, where the trajectory of this connection does not cross the sliding region. It means that it just intersects the switching manifold at crossing points. It happens in continuous systems. There are many works about this kind of connection. The second type of Shunikov-like connection we can consider in this context is when you have still a real saddle focus singularity, but now we have a piece of a sliding orbit making this homoclinic connection. But this sliding orbit is a regular one, so we don't have pseudo-equilibria or things like that. And finally, we have this type of homoclinic connection that is a homoclinic connection through a pseudo-focus that lies on the sliding region of a Filipov vector field, for which the trajectory of this pseudo-focus crosses the tangents line, and we have a fault point here that makes this homoclinic connection in a finite time from the side. This type of connection we are going to call here sliding Shunikov orbit. Douglas has studied this kind of connection, and in this paper, authors have, Douglas and Marco specifically, have shown many interesting dynamical properties of this kind of connection. For example, sliding Shunikov orbit can occur generically in a one-parameter family of Filipov vector fields. One can have, if we have a vector field having this kind of homoclinic connection, then any neighborhood of this Filipov vector field contains infinitely many topological equivalence classes of vector fields near them. And they also have shown that there exists countable infinitely many sliding periodic orbits near this sliding Shunikov orbit. And also, Douglas with Posey and Varon have shown that we can find chaos near this structure. So this connection, as simple as it seems, is very rich when we look to the dynamics near this structure. Then we have tried to find to determine if this kind of connection can occur generically when we perturb some local singularities. The main objective here is to investigate the birth of this kind of connection from a specific boundary equilibrium bifurcation. It means that we have a local study, a local analysis of a boundary hyperbolic singularity. That is a singularity of one vector field that lies at the switched manifold. And when we perturb this system, we ask if this kind of connection can appear generically near the equilibrium that we have perturbed. In order to do that, I will establish some notation, and we will consider a two-parameter family of vector field like this, and I will call this the Z vector field, or the vector field given by equation 1. And we will put some generical conditions or some technical conditions under the coefficients of this vector field in order to reach our goal. In this form, this vector field is pretty generical. We don't have many information. We will just fix that this map here defines a codimension 1 surface in R2. So 0 is a regular value, and we are assuming that when for the unperturbed system, this surface contains the origin, and for the unperturbed system, the vector field has a boundary equilibrium at the origin, and it's a repeller equilibrium where the associated eigenvalues are of this form and lambda 0, where this real part is positive and smaller than lambda 0. And also B0 is bigger than 0. And we will call sigma the, sorry for this mistake here, sigma is the inverse image of 0 from this function h. Sorry for this mistake. Without loss of generality, we will fix that this equilibrium is equilibrium of the x vector field and a regular point for the y vector field. So we will fix these conditions. And just for establishing notation, we will denote by sigma c delta eta, the crossing region, that is the region where both vector fields point to the same side through sigma, and the sliding vector field is sigma s, is the set of points in sigma where the vector fields points to different sides, different sides through sigma. And in this case, since we are doing a local analysis, the vector field y is irregular, so we have a tangency set that contains only points where the vector field x is tangent to sigma. Furthermore, we are considering zs, the sliding vector field associated to the z vector field that is defined on the sliding region, and this vector field can be extended to the frontier of the sliding region by considering this normalized vector field here, which is orbitally equivalent to this one. So we are considering this in order to extend the sliding vector field to the tangent set. Now we are going to assume some pretty technical conditions on the vector field z. Remember that z is a vector field in a generic way. The conditions we have are just on the eigenvalues of the vector field x at the origin. So we define some constants here depending on the eigenvalues of x and on the Lie derivatives of the vector fields x and y. These conditions here in hypothesis H1, they will provide us conditions to guarantee the existence of a pseudo-focus singularity and guarantee that the trajectories of the normalized vector field through the tangent set remains at the sliding set and goes in backward time to the focus. And the first condition, H0, will allow us to put the vector field z in a good canonical form that is given in this first result. So if we have the vector field z given in equation 1, satisfying hypothesis H0 and H1, there exists a smooth change of coordinates and a change of parameters that brings this Filipov vector field to this canonical form here, where we have these conditions on the vector field y, is a regular vector field, and the vector field x starts with this linear part where a is given like this. The most important thing here is that with this change of coordinates, we fix the hyperbolic singularity at the origin, and we give a good expression for the function that defines the switching manifold. It allows us to work with more control of things, because in order to show that connection, we have many things to control. Okay. For this canonical vector field here, this canonical form of the vector field here, we define a new function depending on the flow of this vector field and the flow of the associated normalized sliding vector field. We define this function a that is given by this ugly expression here, but this function here will guarantee, or it will allow us to prove that the trajectories through the tangent line will return to the sliding set. Not this function, but this condition. So we will assume that there exists tau 0 in this interval, such that this function is 0 and this determinant is different from 0. If this canonical form satisfies this hypothesis, we can prove that vector field Z, when we perturb the systems, we have a curve on the space of parameters where that vector field has a sliding Chunikov connection. So if our generic vector field Z satisfies that technical hypothesis and its canonical forms verifies hypothesis 2, we can show that there exists a curve on the space of parameters emerging from the orange of this space parameter, where the vector field admits a sliding Chunikov connection for mu bigger than 0 here. Mu here is the new parameter that we have introduced in the canonical form. Mu is a new parameter that depends on the initial parameters of the vector field Z. So, in order to prove that, we have to control some things. First of all, we have to guarantee that we have one interval or one piece of the tangent set where we have a visible fold singularity, and the sliding vector field has a hyperbolic pseudo-focus here, that is a repeller, and a piece of this tangent set is the trajectories in backwards time of the points in here are entirely contained in the sliding region. After that, we can reduce that piece of the tangent set that we are analyzing to guarantee that the trajectories through the fold points in that region will return to the sliding set. This return is guaranteed by the hypothesis H2 that I defined. And after that, we have to show that some of that returning points will return exactly at the hyperbolic pseudo-focus here. Achieving this, we have shown that we have a sliding Chunikov connection. Okay, so we'll start by considering our original vector field, the canonical form of our original vector field, and we expanded that expression in the parameter mu at mu equals 0, and we may perform a new change of coordinates and a time rescaling. We can put that canonical vector field in this form here, now expanded on the new parameter. And here, for this form, our canonical form is equivalent to this one, just for mu bigger than 0, and in this case, the function that defines the switching manifold is fixed, so it allows us to make some calculation. And we will call this vector field tilde as the auxiliary vector field, and we show that if the canonical form of our initial vector field satisfies hypothesis H1 and H2, then the auxiliary vector field admits a curve. This auxiliary family, this auxiliary family, 2-parameter family of vector fields, admits a curve of sliding homoclinic and sliding Chunikov connection. Okay, but why this result is important? Because when we show that, we can find a curve in the space of parameters where this vector field C tilde admits a sliding Chunikov connection, but this vector field is equivalent to our canonical form of our vector field for mu bigger than 0. So we can recover that information for our canonical form, and from the canonical form, we recover the information for our original vector field, just for mu bigger than 0. So, this slide is just that I have. If our initial vector field satisfies hypothesis H0 and H1, its canonical form also satisfies this hypothesis. In particular, it satisfies hypothesis H1, and if the canonical form satisfies these two hypotheses, then from this auxiliary theorem, we find a sliding Chunikov connection for this family in this curve given by this for mu in this interval. For mu bigger than 0 in this interval, we will have a curve now in the original parameter by recovering the information we had for the. So the problem is reduced to proving the auxiliary theorem. The auxiliary theorem is proved by forgetting that it is associated to the initial vector field and studying it completely, not just for mu bigger than 0. We studied for mu equal to 0, and for mu equal to 0, that vector field is linear. And for this vector field, we can compute the solutions and prove that this vector field has a proper sliding Chunikov orbit. By proving that, and that conditions we have imposed are sufficient to prove by means of the implicit function theorem that there exists that curve where the sliding Chunikov connection happens. And is just there are many pieces, many applications of implicit function theorem for proving all that steps that I illustrated with that images here. We first prove the persistence of the scenario, then we prove the one curve that persists the scenario, and finally we can prove the persistence of the Chunikov connection. And this is the main theorem that we have proved, yet it is a work that is still in progress. And next steps are investigating if, when we change the type of the hyperbolic singularity, if we can get similar results. Another type of boundary equilibrium bifurcation can generate sliding Chunikov orbits. Recently, Almeida and Cespedes have shown the existence of a persistent sliding Chunikov curve for one parameter family of piecewise linear vector fields in Eduarda's master thesis. And these results are coming soon in a preprint someday. And it's our work with Douglas and Oscar. And recently, Leticia and Eduarda, that are here, studied the sliding Chunikov connection in their master thesis, if you want to know more about this. And there are other references where you can find studies on the Chunikov problem or Chunikov connections. In this last work, authors are here, have shown that this kind of connection appear in application models, so it's interesting to study. So, my special collaborators, and gracias. Thank you.
Questions, comments? that very, very nice talk. I have a question about you found this curve of parameters in your parameter space where you have the sliding Cherenkov connection. What do you know about the local dynamics around that in those figures you showed? Are they equivalent, or because you started your talk saying that sometimes you can have an isolated, I didn't quite understand what you meant, an isolated Cherenkov, sliding Cherenkov connection, or do you always have chaos, chaotic dynamics around that connection? Locally.
Locally.
Yeah.
The
Many periodic.
the original, the smooth case,
This one.
under certain conditions on the eigenvalues, we can find chaos.
Okay.
For the Douglas cases. We can produce chaos. I don't remember the conditions, sorry. No conditions. There is always chaos. But always chaos. And what happened? We haven't studied the total bifurcation of the singularity, but when we have this curve, and when we take a transversal curve in the space of the parameters, we expect that the bifurcation that Douglas has shown in his paper preserves. That he has studied this one parameter family where has the Cherenkov connection and bifurcated, perturbed, he break this connection and have a complete study in there. But for this specific model, we haven't finished all the dynamics.
Any more questions, comments? No?
Thanks. Nice talking, Miller. Beautiful girls as well. Congratulations. I'm always interested in these kind of situations, how they differ from the smooth situation, so the smooth Cherenkov in this case. So does your work show anything? So for instance, often non-smooth chaos is robust chaos rather than the kind of chaos we see in smooth systems. So instead of periodic windows and that kind of thing that you see in smooth chaos, you have whole regions of just robust, consistent chaos. And with something like a fold bifurcation, you see sort of slowing down of dynamics and you see a quadratic shape, whereas in non-smooth folds, you see no warning at all and the bifurcation just happens. So do you see any difference in scalings or behavior around these Cherenkov connections that show anything particularly different to the smooth Cherenkov? That would indicate, for example, if you had this in an application, you mentioned it had been seen in some applications, so that indicates something different to what you'd seen in the smooth situation.
Actually, I haven't studied the smooth case with all of his details, just the non-smooth one. But the main difference that I see is that not always we have chaos in the smooth case, but as Douglas have just said, in the non-smooth one, we always can have chaos. So I think we can consider that there is a persistent chaos, a robust chaos. I don't know the exactly word, but in this case here, we just started looking for this specific connection coming from local bifurcations, bifurcation of local singularities. So we are still in progress. We haven't finished all the details or all the properties this kind of perturbation can generate, but I don't know if Douglas has some idea.
I can say so.
just to say the idea of this work is based on a Tereshera paper where she and some collaborators proved the emergence of chaos locally from zero hop fabrication. So that's the main idea. If we were trying to see if chaos in this non-smooth sliding situation can emerge from local singularities. This is
Okay. One more? No? Let's thank the speaker again. So now it's also a pleasure to introduce Professor Otávio Gomide. He's from Universidade Federal de Goiás, and he's talking about an overview of the polycycles in Filipov systems.
Hello. First, I would like to thank you very much, the organization, for the opportunity to talk here. And today I'm going to do an overview of polycycles in Filipov systems. That it's a topic that I am working on at some time. And I will give some notation about no-smoke systems. And then I will introduce the concept of polycycle. And I will explain, I will give you some examples that we have already studied. And then I will talk about a case that myself and Marco Teixeira are currently studying, which is a polycycle at a visible two-fold singularity. Well, now we're going to fix the no-smooth systems, the notation. So we denote by omega r the space of all the vector fields of this form here, where x and y are CR vector fields on R3, and f is a small function having 0 as a regular value. So in this case, the preimage of 0 by f is denoted by sigma, and it is the switching manifold of this vector field. And then we define this switching manifold splits the whole space into two regions, M plus and M minus, where the vector field x acts in the set M plus, and the vector field y acts at M minus. We also make use of the Lie derivative of a function in the direction of a vector field, which is given by this formula here, and also the higher order Lie derivatives, which are inductively defined. This Lie derivative it works as an invariant to measure the contact of a vector field with the switching manifold. And in this way, we denote the tangency set, which are the zeros of the Lie derivative of a vector field, by Sx. So in this case, in order to define the solution of this kind of vector field, we make use of some distinguished regions which occurs when both vector fields x and y are transverse to sigma. And here we have three cases. The crossing region, where both vector fields point to the same side. The stable and unstable sliding regions. In the stable one, both vector fields point to the switching manifold, and in the unstable case, both vector fields point toward the switching manifold. So here we can use the Filipov convention stated by Filipov in this reference, And it says that when we have a point of the crossing region, the local solution is simply the concatenation of the solutions of x and y. If I have a point in the stable sliding region or the unstable sliding region, the local solution is given by the sliding vector field. So we have the vector field, which is defined by the convex combination of x and y, which is tangent to sigma. It is given by this formula. And if I have a point P in sigma, which is not in this situation, we can consider all the curves that are oriented and composed by pieces of orbits of x, y, and fz. So any curve we are considering as a solution. Of course, this produces a lack of uniqueness of solutions. But in this case, to do our study, we don't need this kind of uniqueness. Well, in this context, we have a new class of singularities, which are the sigma singularities. A point P is a sigma singularity of a vector field Z, if it is a tangential point of x or y, which means that one of the lead derivatives, xf or yf, it's 0. Or it is a singularity of x, y, or of the sliding vector field. So here we give some special attention to the tangential type of sigma singularities, which happens under these conditions, which is in the case where we don't have a singularity, but the vector field has a contact with sigma. The importance, of course, the first hint of this kind of singularity is that there is no counterparts in the smooth world. So, of course, it is of major interest. And which it happens that some tangential types, some tangential sigma singularities, they have local stable and unstable invariant manifolds. And of course, this is the study of sigma singularities is a extensively studied topic, which is here I give you 3 references, but of course there are much more than that. But here we have a very complete study of this type of sigma singularities. So here we have some examples in dimension 3. Here we have a fold regular singularity when the vector field x has a quadratic contact with sigma and y is transverse. Here the same situation, but here the fold is visible, here the fold is invisible. And here, of course, we have the Teixeira singularity, which happens when both vector fields has an invisible quadratic contact with sigma. And in this case, when we are in this kind of singularity, under some conditions, we have the existence of this non-smooth diabolo. So here we have the unstable and stable invariant manifolds. Here, in this case, we have this part of the stable, this part unstable, and this part stable. So here we have the local invariant manifolds as in the smooth case. So we ask ourselves, what happens when we have a global connection? So we are leading us to the concept of polycycle. Well, the concept of polycycle is very classic, so we just make some adaptation to the non-smooth world, to the Filipov systems, and here we are consider a polycycle as a set which is composed by a finite union of points in orbits of Z, orbits of the vector field, where P1, Pn are singularities of X. It can be a singularity of X, of Y, or a sigma singularity of Z. And the orbits, gamma 0, gamma 1, gamma I, and minus 1, they must be crossing orbits of Z in such a way that gamma I starts at pi plus 1 and finishes at pi plus 2 to have a kind of connection. We will all see some examples in the following slides. So here, of course, we consider Pn plus 1 to P1 to return to the first point. We have that gamma must be homeomorphic to a circle, and we have that there exists a first return map defined in some non-degenerate region of the space. In this paper, we do a careful study of this kind of definition, and we study some bifurcation diagrams through the study of transition maps. So here we do this in the planar case, but of course this concept also applies to the cases in higher dimensions. So here is the first I think it's the most simple polycycle that we can have in the Filipov systems. That is a polycycle at a fold regular singularity. What is a fold regular singularity? Here I define it rigorously. It is a point of sigma where x has a quadratic contact with sigma at p, and y is transverse to sigma at p. So we have these conditions. In this paper, the authors provided the study of a global connection, a kind of homoclinic-like connection, passing through this point, passing through a fold regular singularity in dimension 2. And they provided a generic unfolding of this polycycle, which is given by this figure. So when we have a one-parameter family, when we have passing through this critical crossing cycle, which is the name that this cycle is known, when we have a critical crossing cycle, when we increase the parameter to m greater than 0, we have the polycycle transforming into a hyperbolic crossing limit cycle. And when mu is smaller than 0, we have a sliding orbit, a closed sliding orbit. So here we have this bifurcation diagram. We have studied this problem in dimension 3, motivated by the simpler case. In dimension 3, we have a main difference, that is the fold regular singularity. In dimension 2, the fold regular singularity is an isolated point. In dimension 3, it does not happen. We always have that fold regular singularity. It happens at a curve of tangential of fold regular singularities. So in this case, we have a more complex situation. And in this paper, we studied a global connection passing through a fold regular singularity in R3. So we have the dimension 3. So we proved that in generic one-parameter families, this polycycle, of course, under certain generic conditions, it unfolds in the same way that we have in the dimension 2. And it's worth to mention that in this case, the image of this fold line through the map, through the first return map, it plays an important role. Of course, here you are seeing that we have that this image must be transverse to the original set. This is a condition that, a generic condition that we must impose to have this kind of unfolding. So here, this is an example of polycycle in dimension 3. Another kind of more complex polycycle that we can have is, of course, the Teixeira singularity. If we return here, when we have a Teixeira singularity with the presence of the non-smooth diagonal, we have, of course, the local invariant manifolds. So, of course, here we can also impose a global connection between them. And under certain generic conditions, of course, we can construct a polycycle. In this case, we don't have only, of course, generically, we don't have only one polycycle. We have to have at least two, or an even number of polycycles. And in this case, we have proved that the presence of this polycycle leads us to a chaotic scenario. In this paper, we do it carefully. So this is this kind of polycycle. We have this diagonal, and we impose a first return. In this case, we can construct a first return map in the switching manifold, and we can construct a horseshoe snail in this map, in this first return map. So here, of course, we can also have this chaotic situation. So we can see here that we can have some simple cases here, but we can have some difficult situations. Well, and now I'm gonna talk about a problem that motivated by this kind of singularities. Of course, we must look to the hyperbolic one, which happens when both vector fields has a visible quadratic contact with sigma. So we have a visible twofold singularity. In dimension 2, this connection, when we consider a connection passing through this kind of singularity, it is already studied by Douglas, Marco, and Iris. And here, in this paper, they studied this kind of connection. This kind of connection is a codimension 2 problem, and we have an interesting phenomenon happening here. Actually, we have a saddle node bifurcation occurring here. We have the presence of two crossing limit cycles bifurcating from this connection, and here we expect this kind of connection to be a bit more complex. Here, in this case, it's worthwhile mentioning that we can construct, of course, a first return map. And here, when we consider the transition map and a diffeomorphism induced by the crossing orbit, we have that this first return map will also be a diffeomorphism. This is not very common in non-smooth systems. But here, as we have the same degree of the singularity, of the degeneracy of the singularity, it happens here. So we expect this to happen in dimension 3. So we start to study this problem in dimension 3. In dimension 3, of course, the first thing that we can think when we talk about a hyperbolic twofold singularity is in the case where the tangential sets are transverse at P. It is the generic case. But when we consider this kind of situation, we have and we start to analyze this polycycle, this singularity in a different scenario, which is the scenario of 5 weakly reversible non-smooth systems. What is a 5 weakly reversible non-smooth system? It is a system that there exists a neighborhood of P and a diffeomorphism phi defined in this neighborhood, such that we have this expression fulfilled for every Q in this set. Also, we have that the fixed point of the maps is contained in sigma, and it sends the part of the neighborhood that is in M plus into the part that is in M minus. So under this hypothesis, we have that if gamma is an orbit of X passing through P0 in M plus, here we have a representation, then phi of gamma of minus T is an orbit of Y in the way we define it here, the reversibility. So in this case, the switching manifold works as a mirror. So it will reflect the trajectory in M minus to M plus, to M minus, and it will reverse the orientation. It works like this. This is an example for phi of XYZ equals XY minus Z, a simple case. Well, when we consider this case, we can think in the transition map of the singularity, which is the analysis of the transition of which is the analysis of what happens locally at the singularity. In this case, when we have this kind of property at a visible twofold singularity, if we consider these transversal sections, sigma epsilons and sigma minus epsilon, we can construct some maps. Of course, in this case, the phi weakly reversibility, it imposes that inside this neighborhood, the tangential sets of x and y, they coincide. So here we don't have the problem of the quadrants. Here we will have a connected component of sigma c of the crossing region working as our domain. So here, in this case, we can construct two maps, T plus and T minus. T plus is a map which goes from S to R, induced by the flow of X. S is a connected component of the crossing region, and R is the image through the flow. So here we have this map. Since we have the mirror property, of course we can construct the map T minus, which goes from K, which is phi of R, into S. So here we construct T minus and T plus. And now we use the phi weakly reversibility. In this case, T minus composed with phi is equal to the inverse of T plus. So in this case, when we consider the composition, which is what we are referring as the transition map, when we consider the composition, we have a nice thing happening. We have that this map is induced by crossing orbit gamma 0, which starts at R0 and it finishes at K0. So we have this beautiful connection here. So in this case, we can also construct the first return map. From here to here, we have the transition map, which we have seen that it is a diffeomorphism. And from sigma epsilon to sigma minus epsilon, we also have a diffeomorphism since we have all regular orbits of x and y, and we have the transversality at these points. So we can construct a map from K to sigma minus epsilon, which is also a diffeomorphism. And of course, it fixes the point K0, which corresponds to the polycycle. So in this case, we can analyze the bifurcation of this kind of polycycle. But of course, we must in this case to restrict ourselves to everything goes in a nice way. We have to be restricted in this work of the phi weakly reversible systems locally. So in this case, when we consider an unfolding of a vector field presenting this kind of polycycle, if we consider a one-parameter family of this presenting this unfolding, we can also provide the same, after following the same steps, we can provide a first return map for every mu in this domain. We can provide a first return map. And of course that all of them will also be diffeomorphism. So here, if we assume that K0 is a hyperbolic fixed point of P0, which is a condition in this polycycle, a generic condition in this polycycle, we have that P mu will also has a hyperbolic fixed point at P mu. So we can find a hyperbolic fixed point. Now we have a problem. Where is this hyperbolic fixed point? If it is in the crossing region, okay, it corresponds to a closed orbit. If it's not, then it's just an extension, and we cannot have a dynamical conclusion about it. So we must analyze it. So of course it depends on the unfolding that we are having. So here we have to impose a generic condition of this unfolding. And the generic condition is that the derivative of the fixed point d mu with respect to mu at mu 0, it's not in the tangent space of the boundary of k at k0. So it must be non-linear. It must be linearly independent with this curve here. In this case, we have that the point p mu, it is depending on mu in one side or in the other side. When it is in this side of this region of this transverse section, when it is in the interior of K, we have that a point p mu corresponds to a crossing limit cycle, which is also hyperbolic from the hypothesis that we have here. And when it is not, in the other case, for the other values of mu, it is not in K. So, in this case, we have this kind of bifurcation diagram, which is very similar with the bifurcation of a fold regular singularity. But here, of course, we are in a very restricted world. So that's why we have this local codimension. So now we can conclude the bifurcation diagram in this case. And of course, we ask ourselves, is there a more general scenario where we can analyze this polycycle? And yes, we can do this in a more general scenario, which is the scenario of locally refractive systems. Of course, the refractive system will also maintain this property that we have the coincidence of the tangential sets. So we have a similar analysis in this case. So here, a non-smooth system is locally refractive if there is a neighborhood of u of p where both lead derivatives of x and y coincides in this neighborhood. So when we have a locally refractive system at a visible two-fold singularity p, we can produce a similar approach that allows us to construct the transition map at this point of this system. And in this case, it is a homeomorphism. Nevertheless, it is not a diffeomorphism. So we don't have the property that we have in the previous case, at least not in general. Here we have an example. Here, a very explicit. Of course, it's not an example of a global connection. It is. I'm talking only about the local property. But here, when we have this simple system, we can construct the transition map in an explicit way. And it happens that the inverse of this transition map is given by this formula here. So recall that the point square root of 2 epsilon 0 epsilon, it corresponds to the two-fold singularity that I'm based on, that is the origin in this case. And here, this map is not differentiable at this function here, it's not differentiable at this point. So if alpha is different from 0, we don't have a small function. And here, it's not even differentiable. Nevertheless, if alpha is 0, this term will disappear, and we have a diffeomorphism, actually the identity. So here, using a coordinate system, we can compute this. I avoid the computations here because they are kind of ugly. But here, if we use a coordinate system, then we can we can characterize this transition map using a kind of normal form. And we have that the transition map is a diffeomorphism if and only if x and y, the vectors x at p and y at p, are anticollinear vectors. So if we have this kind of condition, we have the property that happens in dimension 2. So so the line where the folds point, the direction of the folds, they are imperative in this case to determine the regularity of this transition map. So here in this context, we can apply the same ideas that we applied here to construct a bifurcation and to have the same behavior. Well, this case, it has no counterparts in the two-dimensional case. In the dimensional case, it is always a diffeomorphism. And here in dimension 3, we have this kind of obstruction that this obstruction, of course, arises in the analysis. And now this is a work in progress with Marco Teixeira, and we are analyzing this more general case. Of course, that we have some different tools that we can apply here, as the transition maps that we use in this kind. In this paper here, we provide an analysis which does not involve the first return map, and we change it by a displacement function. And this is the way we are planning to proceed in this, to analyze this kind of cycle. But here the expressions are not very friendly, so we still have a work to do. Well, that's it that I wanted to talk to you, and thank you very much.
Comments, questions? Very nice talk. Can you say something about the local dynamics around the polycycles? Like in the three-dimensional case, what's happening? Are they isolated? Do they?
In this case here. Yes, in this case we have the same. It works actually like a hyperbolic limit cycle. It's the same way. So here we have a first return map. So it depends of the behavior of this point, of this hyperbolic point. For example, if this is a saddle, of course we can have only a part of the saddle, because a part of the saddle is hidden, since we have this more special domain. But here, when it comes to here, this will be also a saddle point. So we have a limit cycle of saddle type. So the type of the hyperbolic singularity persists and characterize this kind of system. So we can display any of this kind of phenomenon.
Okay. Any more?
Sorry, I thought I might have spoken my last about twofold singularities, but it seems they won't go away. You promised to show these polycycles at a proper visible 3D twofold singularity, and then you left the problem and went to the reversible systems and the refractive systems, which made sense to do first. But I didn't really understand what the problem was with the visible twofold. So they would return. You said you needed them to go through the crossing regions, but if they land through the sliding regions, this is actually the one situation where you don't have too many problems. They'll slide, they'll go to the next fold, if I remember right, and I try not to anymore. The only singularity, the only trajectories that pass through the twofold point are a zero measure set in this case. So this is a fairly nice case to do the full case, so I was wondering what the problem was.
Yes, in this case, which is the most common case, this is the first case that we want to analyze. Here the problem is that here we have this kind of situation, and we have these two quadrants in the crossing region. So when we consider a global condition, of course, this is kind of the same problem that it happens here. It's not very different. But there is an analytic complication that here we can also, for example, the Vichy coordinate system, and we can have an expression to this fold here, a complete expression. And of course, since here we have a transverse kind of thing, it is easy to construct this expression. Here we don't have the same luck, because of course we can provide a part of this map by Vichy coordinate system, but the other case no. The other case we have to work with the expansion of the map. So here, when we work with this expansion, the image of this kind of these tangential sets, they are a bit complicated. There are many parameters to analyze. So we don't know where this quadrant is going through the first return map. That's the problem. It's not a problem in the approach. It's a problem in the analysis of the problem.
Okay, fair enough. Are you familiar with Nordmark mappings and Nordmark's local discontinuity mappings for dealing with the bifurcations that you've got as a polycycle or a periodic orbit passes through a fold point?
No,
There's something which
about normal maps, but
I think they break down at the kind of points you're looking at, but they could be at least useful to check out as well.
if you can send me, I would be very great.
Anyone? No? Let's thank the speaker again.